Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 1.4 on matrix equations. I'll teach you all about the 7 topics listed here, and by the end of this video, you'll have a much better understanding of how to write a linear system of equations as a matrix equation and how to solve a matrix equation. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. We'll begin by talking about matrix vector products. A matrix vector product is just a matrix times a vector and is used in solving a linear system of equations when we write a linear system as a matrix equation. The linear system of equations that I've listed here has 3 equations and 3 unknowns. To write this linear system of equations as a matrix equation, we'll put all the A's into matrix A. That's going to look like A11, A12, A13, A21, A22, A23, and then our last row, A31, A32, and A33. We'll now put all the x's into vector x. Our x's are x1, x2, and x3, and then we'll put all the b's into vector b, and those entries are b1, b2, and b3. Our matrix equation is then our matrix A times vector x, and that's going to be equal to vector b. Matrix A times vector x is called a matrix vector product, and it'll be defined if the size of A matches up with the size of vector x. A is a matrix, and x is a vector. In the example that we had above, A was a 3 by 3 matrix, but in general, A can be written as an m by n matrix. The only way that we can multiply A times x is if x is an n by 1 matrix, because these two numbers need to be the same. Let's look at these 2 examples to see how this works. We're going to look at the sizes of our matrix A and our vector x and see if the product is defined. In our first example, our matrix A has 3 rows and 2 columns, so it's a 3 by 2 matrix, and our vector x has 2 rows and 1 column, so it's a 2 by 1 matrix. These 2 numbers are the same, so our product is defined, and the size of our product is going to be 3 by 1. We just ignore these inner numbers, and our size comes from the first 3 and the last 1. Let's now look at our second example. Let's label this our matrix A and this our vector x. The size of A is again 3 by 2, but this time the size of x is 3 by 1. Notice that these 2 numbers are different, and because of this, we say that our product is undefined. Now that we know how to determine if we're able to multiply a matrix times a vector, we need to learn how we can multiply a matrix times a vector. We're actually going to learn 2 methods to multiply a matrix A times a vector x. The first method is called the linear combination of columns method. You may also see this referred to as the definition. This method views the vector x as a set of weights for the columns of the matrix. In this method, we're going to write A in terms of its columns. We'll write A as column A1, A2, all the way up through AN because we have n columns. Our A's are column vectors. To multiply A times x, we'll multiply the columns of A by the components in our vector X. Here's what this looks like. We have our A, which is our column vectors A1, A2, all the way up through AN, and we're going to multiply this by our entries in X, and those are X1, X2, all the way down through Xn. We'll multiply X1 times A1, and then X2 times A2, and then all the way down through Xn times AN. This gives us the formula X1A1 plus X2A2 all the way up to Xn A sub n. The X's are our weights, and our A's are our columns of A. Let's highlight this formula because this is a formula that we're going to use when we need to multiply a matrix times a vector using the linear combination of columns method. Let's see how to use this formula by walking through this example problem. We're going to compute the matrix vector product using the linear combination of columns method. When I multiply a matrix times a vector, I always like to begin by seeing what the size of our answer will be. In our first example, we have a 3 by 2 matrix A and then a 2 by 1 matrix X, so our answer is going to be of the size 3 by 1. Following the formula above, we're going to multiply X1 times our first column, which is A1. This gives us 7 times the vector 1, 2, 3. And then we'll multiply X2 times our second column. This gives us 8 times 4, 5, 6. This gives us an answer of 39, 54, and 69. You might want to stop the video and see if you can do the next example on your own. Let's start by finding out what the size of our answer will be. We have a 2 by 3 matrix multiplying a 3 by 1 column vector, and that's going to give us an answer that will be 2 by 1. We're going to multiply X1 times our first column plus X2 times our second column, and then X3 times our third column. This gives us 1 times 1, 4, plus 2 times 2, 5, plus 2 times 3, 6. Our answer is then 11, 26. The second method that we'll use to multiply a matrix times a vector is called the row vector rule or dot product method. Instead of writing A in terms of its columns, for this method, we're going to write A in terms of its rows. A will be row 1, and then row 2, all the way down to row M, because we have M rows. Let's just make a note that our R's are row vectors. R1 is just our first row, which is A11, A12, all the way over to A1n. Notice that the size of R1 is a 1 by n matrix. Before we write down the formula for this second method, we need to learn two new concepts. The first is called the transpose of a matrix. The transpose of a matrix switches the rows and the columns of the matrix. Since R1 is a 1 by n matrix, R1 transpose will be an n by 1 matrix and look like this. The capital T stands for transpose. Let's also remind ourselves what X looks like. X is X1, X2, all the way down to Xn. When we multiply matrix A times vector X, we'll take the first row of A and multiply it by vector X. This gives us R1 times X. We'll then do this for all the other rows, and we'll get R2X all the way down to Rn times X. To multiply R1 times X, we need to understand what the size is going to look like. R1 is a 1 by n matrix. X is an n by 1 matrix. So our answer is going to be a 1 by 1 matrix, which is just going to be a number. This is going to be defined as R1 transpose dotted with X. This is called the dot product. It's just an algebraic operation that takes two vectors of the same size and returns a single number. R1 transpose is an n by 1 column vector just like X. If we look back up here, we can see how we can evaluate this dot product. We're just going to multiply A11 times X1 and then A12 times X2 all the way down to A1n times Xn. Let's write this down. We have A11 X1 plus A12 X2 all the way up to A1n times Xn. In our matrix vector product, this is just A11 times X1, A12 times X2, all the way up through A1n times Xn. Let's go ahead and highlight this formula because this is the formula that we're going to use when we have to multiply a matrix times a vector using the row vector rule or dot product method. Let's now do an example where we'll compute two matrix vector products using the row vector rule or dot product method. Notice that these are the same examples that we did when we used the linear combination of columns method. To compute this product, we're going to multiply row 1 times X, and then row 2 times X, and then row 3 times X. We'll first multiply row 1 times X. This gives us 1 times 7 plus 4 times 8. Let's now multiply the second row times X. This gives us 2 times 7 plus 5 times 8. And then lastly, we'll multiply the third row of A times X. This gives us 3 times 7 plus 6 times 8. When we do the multiplication and add it all up, we end up with 39, 54, and 69. Just like before, I'd encourage you to stop the video and see if you can do this next one on your own. For this example, we're going to multiply row 1 times X, and then we'll multiply row 2 times X. We'll first multiply row 1 times X, and that gives us 1 times 1 plus 2 times 2 plus 3 times 2. We'll then multiply row 2 times X, and we'll get 4 times 1 plus 5 times 2 plus 6 times 2. This gives us an answer of 11 and 26. We'll now quickly go over two properties of matrix vector products. A is an m by n matrix, and then U and V are vectors in Rn, and C is a scalar. Our first property tells us that when we multiply a matrix times two vectors that are added together, we can multiply that matrix times each vector separately. This gives us A times U plus A times V. Our second property tells us that we can multiply a constant times a vector and then multiply it by a matrix, or we can choose to multiply the matrix times the vector first and then multiply it by the constant. Now that we know how to multiply a matrix times a vector, we can learn more about the matrix equation AX is equal to B. Our A is an m by n matrix. X is an n by 1 column vector, so it's an element of Rn. And then B is an m by 1 column vector and is an element of Rm. That's because when we multiply m by n times n by 1, we end up with an m by 1 matrix. Let's now do an example. If A is a 2 by 4 matrix, we want to determine what the size of X is and what the size of B is in our matrix equation AX is equal to B. We'll begin by writing down AX is equal to B and then filling in the sizes that we're given. We're told that A is 2 by 4. We want to know what X is, so we'll just write it down as X, and then we want to know what B is. The only way that A can multiply X is that if X is a 4 by 1, because these two numbers need to be the same. Once we know what X is, we can figure out what B is. We're going to ignore these numbers, and then B is going to be a 2 by 1. So our answers are going to be that X is a 4 by 1 matrix, and it's an element of R4, and B is going to be a 2 by 1 matrix, and it's an element of R2. We now know 3 ways to write a linear system of equations. We can first write it as a matrix equation. That looks like A times X is equal to B. We can then write it as a vector equation where we multiply the X's by the columns of A. This looks like X1, A1 plus X2, A2 all the way up through Xn, An is equal to B. Third way that we can write it is an augmented matrix. And that's the way that we learned at the beginning of this course. We have A1, A2, all the way up through An, augmented with B. All 3 of these ways to write a linear system have the same solution set. At different times in this course, we'll be writing our linear system in one of these 3 different ways. Let's now do an example where we'll write our given linear system of equations as a vector equation, a matrix equation, and as an augmented matrix. I'm going to choose to write it as a matrix equation first. This is going to look like our matrix A, which is 8, 5, 1, minus 1, 4, minus 3, times our vector X, which is X1, X2, is equal to our right-hand side B, which is 4, 1, 2. Let's now write it as a vector equation. We have X1 times the first column of A, that's 8, 5, 1, plus X2 times the second column of A, minus 1, 4, minus 3, and that's going to be equal to B, which is our right-hand side, 4, 1, 2. And then lastly, we'll write it as an augmented matrix. 8, 5, 1, minus 1, 4, minus 3, and then augmented with 4, 1, 2. I'm I'm now going to teach you how to write the solution to a matrix equation in terms of a vector. It's easier often to visualize what a solution looks like if we write it in vector form. Suppose the solution of this linear system is x1 is equal to 1, x2 is equal to 3, and x3 is equal to 4. We often refer to this formulation of the solution as writing the solution explicitly as a general solution. We can also write our solution as 1, 3, 4, and this is often called the comma delimited form. Now we can also write it as a vector. So we would say vector x is equal to x1, which is 1, x2, which is 3, and then x3, which is 4. And as you might guess, this is called vector form. Let's now do an example where we'll use an augmented matrix to solve the matrix equation and then write the solution as a vector. Let's put A and B into an augmented matrix. This gives us 1, 3, minus 2, 2, augmented with 1, 19. We want to then solve the system, so we're going to take our augmented matrix and put it in reduced echelon form. I'm not going to go through the steps here, but this is what we end up with. Our matrix looks like this: 1, 0, 0, 1, augmented with 5 and 2. We have a pivot in every column, so that tells us that we have a unique solution, and that unique solution is x1 is equal to 5, and x2 is equal to 2. So our solution in vector form looks like x is equal to 5, 2. Let's now look at our second example. We'll put A and B into an augmented matrix. And then reduce it to reduced echelon form. Our reduced echelon matrix looks like this. We have 1, 0, 0, 1, 5, minus 3, augmented with 8 and minus 2. We have 2 pivots, and then we have a column without a pivot. That means that we're going to have infinitely many solutions. Our x1 is equal to 8 minus 5x3, and then our x2 is equal to minus 2 plus 3x3, and our x3 is free. To write this in vector form, we'll start by writing down x is equal to x1, x2, and x3, and then we'll plug in these equations. x1 is 8 minus 5x3, x2 is minus 2 plus 3x3, and then x3 is free, and this is usually the part where students always get confused. You just put in x3 as itself. This gives us the solution 8 minus 2, 0. Notice that there's no constant in our third entry, which is why we have a 0. And then we'll pull out our x3 and multiply it by minus 5, 3, and 1. In section 1.5, we're going to talk a lot about the geometry of these solutions, now that we know how to write them in vector form. When we talk about solutions to a matrix equation, we often want to determine if our matrix equation has a solution for all possible B. This is called the existence of solutions. If we find that our equation doesn't have a solution for all possible b, we'll want to describe the set of b for which it does have a solution. In our first example, we'll find that our matrix equation has a solution for only some b. And in our second example, we'll find that it will have a solution for all b. Let's work through this first example. We'll begin by putting A and B into an augmented matrix. Since we're looking to determine if our equation has a solution, we're going to take our augmented matrix and reduce it to echelon form and then look at the pivots. Since we've never done a problem like this before where we have variables on our right-hand side, I'm going to go ahead and walk through all the steps. We'll begin by working off this pivot and getting zeros below it. This gives us 1, 1, 2, B1, and then 0, -1, -1, B2 minus B1. And then for our third row, we'll get a 0, a -1, a -1 again, and then a B3 minus 2 times B1. We'll now work off this pivot and get a 0 below it. This gives us 1, 1, 2, B1, 0, -1, -1, B2 minus B1, and then 0, 0, 0. And now we have to think. We're multiplying our second row by -1 and adding it to our third row. So we have B3 minus 2B1 minus B2 plus B1. Notice that we have a row of zeros on the left-hand side. That means that we're going to have to make sure that this expression involving our b's is equal to 0 if we're going to have a solution. So we have B3 minus B1, we're just combining the B1s there, minus B2 is equal to 0. So we'll say that a solution is going to exist if B3 is equal to B1 plus B2. We can think of our B as looking like this. We would have B1, B2, and then instead of having any B3, we would be restricted to having our B3 be B1 plus B2. That's why for this example, we don't get a solution for all B. We only get a solution for B that is in this form. We can also think about this geometrically, and we can view this equation as a plane, so our only solution will be in that plane. Let's now look at our second example. I've already done all the work for this. We put our A and B into an augmented matrix, and then we put it in echelon form. Notice that every column had a pivot. This tells us that we're going to get a unique solution. Since every row has a pivot, we have no row of zeros and then no restrictions on what our b's can be. Because of this, we say that we're going to have a solution X for all values of b. The last and very important topic that we're going to talk about is the equivalence theorem for an m by n matrix. This theorem helps us understand more about the matrix equation AX is equal to B. All the statements in this theorem are either all true or all false simultaneously. The really nice thing about this is if you know that one statement is true, you'll know that all the other statements are true. We'll understand this theorem better if we'll first write down the sizes of A, X, and B. Just as a reminder, A is an m by n matrix, which means that X is an n by 1 column vector and B is then an m by 1 column vector. So we say that X is an element of Rn, and then B is an element of Rm. Let's now go over the 4 statements in our equivalence theorem. Our first statement says that if for each B in Rm, the equation Ax is equal to B has a solution. If this statement is true, then our next 3 statements are also true. Statement 2 says that each B in Rm is a linear combination of the columns of A. This means that B can be written as A times X. Our third statement tells us that the columns of A span Rm. This just means, in terms that you might have already learned, that the span of the columns of A is all of Rm. And then our last statement says that A has a pivot position in every row. If we have a solution for every B, it has to have a pivot position in every row because we can't have a row of zeros. Let's look at example 2 from the previous page to help us understand this theorem. In this example, we found that we had a solution for all B. We could write B as A times X. Every column had a pivot, which means that the span of the columns of A is all of R3. And then lastly, A has a pivot in every row, which means that we'll get a solution for all B. Thanks for hanging in there with me. We learned a lot of material in this video. Be sure to check out the next video in this series, where I'll teach you all about how to balance chemical equations using linear algebra.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.